Okay, so now we will look at the Pearson's correlation measure. This Pearson's correlation coefficient will give you a quantitative measure of the extent of linear relationship between two variables. So in the sense that if the correlation coefficient is closer to positive 1, it indicates the two variables have a positive linear relationship. That is, if one variable value increases, the other variable value increases also. Similarly, if one variable value decreases, the other variable value also decreases. Now, if the correlation coefficient is closer to negative 1, then we can say the two variables have a negative linear relationship. That means if one variable value increases, the other variable value decreases, and vice versa. On the other hand, if the correlation coefficient is closer to 0, then we can say there's no linear relationship between the two variables. So that means if one variable value increases or decreases, we cannot say anything about the other variable. So again, like the other measures, this is going to be in a certain range, and the correlation coefficient is going to be in a range of negative 1 to 1. So once we confirm the linear relationship between the two variables by measuring the correlation coefficient, then we can proceed with what is called the regression analysis to predict the value of one variable using the value of the other variable. So let us continue with the weight and height example of social network of users. So we have 7 users, weight and height values, and we'll now determine the Pearson's correlation coefficient between the two metrics. Now this is a formula for the Pearson's correlation coefficient. So x and y are the two variables. So here x is say our weight and y is our height. So as we can see in this formula, it involves the average weight on the average of x and average of y, and you also have to find the difference between the individual values of the variables, say x, and the average x, similarly the individual values of the variable y and the average y, and then square those differences as well as take the product of those differences. So let us see how to do the calculations here. So you have the 7 vertices, the raw weight values of course, and the raw height values. So as I said, let us consider the x as weight and y as height. So we are going to take the average of the weight values. So average of all the 7 integers is going to be 152.3, and then you have to find xi minus x bar. So that means the individual weight values minus the average of weight values. So 130 minus 152.3 is negative 22.3. 150 minus 152.3 is negative 2.3. 125 minus 152.3 is negative 27.3, and so on. So now once you find the difference in the weight values, you have to also find the square of the differences. So square these differences. So negative 22.3 square is this, negative 2.3 square is this, and so on. Now we have to find the sum of these squares of the differences. So this is the sum of these squares of the differences. So repeat the calculations similarly for the height. So take the average of the height and find the difference between the individual height values and the average height. So 55 minus 67.4 is negative 12.4. 75 minus 67.4 is 7.6, and so on. Then find the difference in height square. So square the differences in height and then sum those squares of the differences. Now you also need the product of the differences. So take the product of the differences between the height and weight. So that's this. And then you need the sum of the product of the differences. So sum the product of differences, we get this. So now plug in these values to this formula. So sum of the product of the differences is 1477.14. Sum of the squares of the differences for the weight and height is going to be 33391.43. So take a square root of that. Similarly 773.72, you have to take a square root of that. So if we do the math, we get 0.9118. So as I said, If it's closer to 1, that means there's a linear relationship between the two variables, in this case weight and height. So now we can go ahead and do the regression analysis. So we will plot the weight versus height. As I said, weight is our x and height is our y. So we'll try to predict height based on the weight. So if we plot in Excel, so I have also shown here, I have the values here. So you can highlight the variables values, click on the chart. Of course, how you do exactly these steps depends on the Excel version, but pretty much they should be the same. So now you have got the plot of weight versus height. So now right click on by clicking any of the data points and choose the add trendline option. You want to do the linear assessment, so let us stay with linear. Go to the options and click on display equation on chart and display R square value and chart. By the way, this is 2003 Excel, so how you do this in 2007 Excel or 2010 might be a little different. So this is our linear relationship between the weight and height. So as I said, the height is our y variable. So height is 0.4356 times weight plus 1.1003. So that's our intercept. So this is a linear equation like y equals mx plus c. So the c is the intercept, m is the slope. So this is the slope 0.4356. So using this equation and the actual weight values, we can predict the height values, and we'll do that quite soon. And before we do that, what is the measure of accuracy of this prediction? So Excel will also display an R square value, and in this case we get 0.8315. So what is this R square? R square, the square root of R square is our Pearson's correlation coefficient. So if I take a square root of 0.8315, you're going to get this 0.9118. So R square is a measure of the proportion of variation in the dependent variable that is predictable from the independent variable. Okay, so how much you can predict the variation in the dependent variable, which is your height or y, based on the independent variable. Okay, so basically how accurate is this prediction? That's what R square captures. Okay, so let us go ahead and do this prediction. So this is our linear relationship. The predicted height is 0.4356 times the actual height plus 1.1003. So what we'll do is we'll use actual weight values in this formula and predict the height. So for these weight values, these are the predicted height. So now what we will do is we need to compare the actual height with this versus the predicted height and see what is the error in the prediction. Alright, so for that we need to normalize the two things, actual height and predicted height. So we use the sum of the squares approach. Square root of the sum of the squares approach. So basically what we need to do is find the squares of the actual height, which are these numbers, sum them up and take a square root of the sum of the squares. We get 180.6. So divide now each of the individual actual height values by 180.6. So 55 divided by 180.6 is 0.3045. 75 divided by 180.6 is 0.4153, and so on. Now do the same thing for the predicted height. Square the predicted height values, take the square root of the sum of the squares, it comes out to be 180.2. Now divide the individual values by 180.2, we get these as the normalized predicted height values. So now what you do is find what is called the residuals, which is the difference between the actual height, the normalized actual height, and the normalized predicted height. So these are the residuals. Then square these residuals, we get these numbers. Then take the square root of the sum of the squares of the residuals. So square root of, so the sum, so sum these squares of the residuals Okay, so these are the actual residuals. It is simply the difference between the normalized actual height minus normalized predicted height. Then square of this residuals, these are the numbers. Sum these squares, take a square root of that sum. We get 0.06326. So this is called the standard error of residuals, and its value is going to be in a scale of 0 to 1, and what we got here for our prediction is 0.063 or something like that, which is pretty much closer to 0, indicating your regression analysis is very accurate. So I'll stop the video with this.